Hello, in this session we're going to cover strength design of concrete masonry. My name is Sam Rubenzer. I'm the founder of Force Consulting and the man of a professional engineer in several Midwestern states. I have my engineering degree from the University of Minnesota, my MBA from Marquette University. Here at Force, I lead a team of engineers with a lot of different masonry design experiences. We've been consultants to the masonry industry for about 15 years and create a lot of papers and presentations such as this one. For the presentation today, what we're going to do is we're going to cover a lot of information about strength design for masonry. A lot of the information that we're going to cover comes from the code book, the Masonry Society TMS 402602, the 2022 version. You can see the link for the standard where you can download, you can order the book, or you can actually view the standard online. So the TMS 402 is going to be the building code requirements, and then the TMS 602 is going to be the specification for masonry structures. Learning objectives for today, we're going to be looking at the fundamentals for masonry load demands on buildings, basically where masonry can be used in buildings, what are the different types of loads on those elements, and then what are some of the capacity equations for walls, in-plane, out-of-plane walls, lintels within walls or beams, columns that you can have, and then we'll look at an example with strength design considerations. What do we have within concrete masonry? We have different concrete materials. We have concrete masonry units. We have concrete mortar and concrete grout that's going to be utilized for comprising of the different concrete elements in a masonry wall. We also have reinforcement. We have vertical bar reinforcement that can help with the flexural capacity. We have horizontal joint reinforcement and horizontal bar reinforcement for both crack control and strength design. Really, when we look at masonry, we try to understand what the actual strength is of masonry. We have concrete masonry units from a variety of producers across the country. We can see strengths from those different producers. We can get test results and reports for what the actual unit strengths are going to be. Utilizing the Table 2 of the TMS 602 code for those concrete masonry units, we can define a mortar type, and from that, we can get an overall strength of concrete masonry, the F''M. So again, we need to learn about what the unit strength is. We can specify what the mortar strength is going to be, and then we can design to an overall F''M. You can also select to use higher strength units than what's typically produced. You can certainly specify an even higher concrete masonry unit than what might be locally available. Obviously, there's cost implications, but we can design with and use higher strength masonry units. We can specify type M or S mortar to get F''Ms all the way up to 4,000 PSI for strength design. Within buildings, we know that we can use masonry in a variety of places. We have foundation walls where we can have basement walls or stem walls. Any place that we go below grade, we know that we can use masonry for supporting the walls above or different elements above. We know that we have shaft walls for stair and elevator shafts. Those can actually be used for a variety of purposes. Obviously, architecturally, they're the main egresses out of a building, but also they're going to be needing to be fire protected. Those walls, whether they be shaft walls or interior or exterior walls, can also be bearing walls and shear walls. We also have non-load bearing exterior walls and non-load bearing partition walls. So a lot of different types of ways that we can use masonry within different types of structures. And then we know within the buildings, again, we have a variety of different loading conditions that we have to check our masonry designs for. We have axial forces that we have on walls. We have moments. We have in-plane moments, out-of-plane moments. And then we also have shear stresses and forces that we have to check. What are axial forces? Again, stepping back to the basics here a little bit, any vertical load that you're going to be placing on a wall element or on any element is going to cause those elements to want to compress or push together. That stress, that compression is something that we need to check for concrete masonry design elements. Conversely, we also have lateral loads that can be applied to elements within a building. When we apply that lateral load, what we end up with is bending stresses, but those bending stresses can be looked at as a couple force. One area of a wall element would be in tension, where it would be almost pulling apart. We have another part of the wall that would be in compression. So again, if you look at the lateral load from the left onto a wall, you're going to notice the compression forces. Everything's going to be compressing together on the left side. And the far side of the wall, everything's going to want to spread apart and more of the tensile stresses. So if we look at this on a smaller scale, we can see that bending forces, we can have that positive and negative tension and compression stresses that can act on our element. But when we combine those forces or stresses with additional loads, maybe load-bearing vertical loads on a wall, sometimes we can have the net compression forces being what's resulting for both the bending and vertical load that you can have in design. And certainly that's going to be good for a material like concrete or concrete masonry, because concrete masonry are going to be very good in compression, but not so good in tension. So we know that we can resist much higher stresses and forces in a compression capacity. But if we go into tension, in masonry, we do have tensile properties that we can utilize for an unreinforced masonry wall. But typically, if we want to gain more capacity, we're going to utilize other material to gain more tensile stress capabilities within our designs. Certainly, we do have partition walls. Are good examples of walls that can be remaining unreinforced. But for the most part, this presentation, we're going to focus on reinforced masonry designs. So that's, again, if we have the bending load and we have vertical load, but we end up with some net tension in our design. Again, we know that we have concrete masonry elements that are very good in compression, but the addition of reinforcement does give us a lot of capabilities in terms of having a much higher capacity overall section. So again, masonry is good in compression. Reinforcing steel is very good in tension. So that the combination of the two does give us a nice, strong overall section. Again, bringing this back into our table, looking at the different masonry elements that we might want to look at. Axial forces, anytime that we can have an element that's going to be, the primary forces are going to be axial. We know that the masonry material is going to do pretty well in those applications. Anytime that we do have moment and shear, where we have lateral forces, we know that we have some tension and compression that's going to be created, so that we know we maybe have to move into reinforced masonry elements to gain the full capacity that we are looking at for that design. So again, masonry is very good in compression, axial compression. Utilizing steel is what allows it to be very good also for bending moment. For shear, masonry is also very good in shear. And typically we are able to resist shear forces, whether they be in a lintel or in a shear wall, with just the masonry material, the concrete masonry material. But we do have the option to gain additional shear capacity with reinforcement as well. So again, getting back to some more of the basics about definitions of elements, masonry walls are going to be anything that's going to be 3 times longer than it is thick. So an 8-inch thick masonry element's going to need to be 24 inches long to be considered a masonry wall. 12 inches thick, 36 inches long. You can see the pattern. Load-bearing walls are going to be anything with 200 pounds per foot in addition to self-weight. We also have other definitions for and other code provisions for shear walls. Within the TMS code, we know that shear walls are going to be elements that have reinforcement. We have ordinary and intermediate and specially reinforced masonry shear walls. All of them have slight differences in the reinforcement requirements that are going to need it, and different areas, seismic design areas that would be where the walls are able to be utilized. We also do have, again, masonry column elements, where we have the code defines the actual size of the column element. It needs to be at least 8 inches on each side, needs to have a certain reinforcement ratio, minimum of 4 bars and lateral ties of a 1/4 inch diameter or more. So again, it doesn't start with number 3 bar, a 3/8 inch diameter. It actually starts with a 1/4 inch. So you could, in theory, use a number 2 tie bar, which would then fit well within the actual mortar joints. just a little note for later. But the other thing about columns is there are lightly loaded column provisions since the 2013 code for seismic design categories A, B, and C, less than a 2,000 pound axial gravity force, no more than 12 feet high. So in that situation, we can just use one number 4 bar in those small column elements. Masonry lintels, we have bottom bars that we typically are going to see within a masonry lintel. Bottom bars that are going to be there for the positive bending moment that you would have for a lintel design. If you are looking at that lintel as a simply supported element, certainly it's going to be all positive bending moment. You also could have top bars, though. If you look at the lintel element as a fixed end condition, you would have negative moment at each end, and you would have perchance the need for top bars. Anytime that you would have a lintel also within shear wall, you maybe would have load reversals where you could have top or bottom stresses and forces that you maybe need top and bottom bars throughout the whole length of the lintel. Other places that we need to consider using top and bottom bars is if we have a high lateral load, sometimes using a balance of top and bottom bars for an out of plane bending for the lintel would be prudent. We know within lintels, we also have stirrups that we can utilize. Typically, we would want to add more depth and simply add more concrete masonry to have better shear resistance. We typically wouldn't use stirrups within a concrete masonry lintel unless necessary. If we have a limited depth to the actual lintel size, we know that we can add stirrups. We can add single leg or double leg stirrups for increasing the shear capacity. We know that when we look at the lintels, we have different varieties of analyses that we could do. We could do a finite element analysis, or we could do a more traditional, simple analysis where we would take into some provisions from the code about span length and overall deflection requirements, so on and so forth. So for masonry lintels, we know that we have material that works very well with the overall wall around it. We know that we can have very high-performing lintels and wall systems. They do work very well together and very integral with one another. There's not going to be anything within the code that's going to set any size restrictions, so there's no length restrictions. And really, honestly, the longer the lintel, the more the lintel makes sense to be masonry and not some other material. So we definitely know that masonry lintels are going to be very good component to the overall masonry wall system design. Last little piece of information here about code requirements for reinforcement. We have reinforcement bar sizes that should be number 9 bars or less within the strength design provisions. And just from a practical perspective, using anything larger than a number 9 might be pretty difficult to construct, so that we know that a number 9 is a good practical limit as well as what is in the code and what has been tested. We also have bar diameter to be less than 1/8 of the overall wall thickness and bar area to be less than 4%. And then there's other provisions about the actual bar area relative to lapped areas and stuff like that for reinforce. So reinforcement, we do have some limitations for what we want to use. Again, it's always good to remember that you're placing this reinforcement within confined cells, and so making sure that we have some prudent selection of reinforcement relative to the different open cell areas that you'd have within your masonry wall. So masonry is a system. We can see that we have concrete masonry units, mortar and grout, all the different concrete parts of the masonry design. We have vertical and horizontal reinforcement that we can consider to make bending or shear or axial load equations from. And we know that, again, within the different elements, we have walls, different types of walls, shear walls, partition walls, load-bearing walls. We know that we have lintels within those walls for the openings that we have, and we know that we can use columns and pilasters for supporting high axial forces within our designs. So next, we're going to take a look at what we have for strength design versus allowable stress design. Just a few notes on the differences between the two. Certainly looking at the strength design provisions, loads on a building are either permanent or transient. Strength design puts a higher factor of safety on the less predictable transient loads. And so certainly that would be a good understanding for why strength design tends to make sense to some people. Another thing to think about, since we often have people that compare the strength of concrete to concrete masonry, looking at some of the similarities that you would have code-wise. The allowable stress design hasn't been really utilized for concrete design since before 1970. It's still ASD is still probably the more common method for doing masonry design today. But again, if we were trying to bring those kind of into parallel with one another, concrete is obviously what strength design is based on today, and it's certainly a good reason for why to consider it also for masonry as well. Even if it might be a little bit less common today, I think it still makes a lot of sense to consider, especially as we're comparing it to concrete designs, which are very similar. So ASD is going to be comparing the actual and allowable stresses. Stresses typically kept below the yield load for the member by computing member load capacity as divided by nominal strength divided by a factor of safety. And then strength design is going to be looking at the required strength to the actual strength, looking at the combined forces kept below the computed member load capacity as a product of the nominal strength times the resistance factor. So looking at the different tech guides that are available and some of the different diagrams to show what a section looks like and some of the stress analysis that is done within allowable stress design based on your reinforcement location and allowable stresses that you would have for both the concrete masonry and the steel reinforcement that you would utilize. And then strength design. Again, strength design going to be very familiar, especially if you're used to doing concrete design. The capacity equations, stress strain distribution to force diagrams that you'd have within strength design are going to be very similar to what we have seen for concrete design. For strength design, predictability of the applied loads through use of load factors is going to be defined. We have material and construction variability that's addressed through resistance factors. We separating the factor of safety. We have independent load factors, resistant factors, and more consistent effective factor of safety would be attained. The result, I think, can be a safer or lighter structure depending on the predictability of the load. Obviously, things that are going to be governed more by dead load design situations, can certainly have a lower factor on those elements. You could have a much lighter, more efficient design, stuff that's going to be governed by more of the transient loads, the live loads, the wind or seismic loads. If those are going to be more of the primary elements, then certainly it's going to be a safer design, I would think, for strength design. So it tries to put the more importance on the less predictable load situation. So factored designs must not exceed nominal capacities reduced by phi factors. Again, the quotient of the load factors divided by phi factors analogous to the safety factor of allowable stress design that could be comparable to, and should be comparable to that safety factor. So again, just looking at the two and the differences between the two, what we would utilize for considering strength design. If we do look at strength design, certainly looking at some of the different properties that you would utilize for the strength of the reinforcement, Fy equal to 60 KSI would be very common. Strength of masonry, again, that's going to be variable across the country here. We just selected an F'(M) of 2250 for design. We know that we have different factored load cases and forces that we would want to utilize from ASCE 7. Some of the different definitions, F'(M) is going to be the compressive strength of masonry. We have F'G, which is going to be the compressive strength of the grout. Fr is going to be the modulus of rupture. Fy is going to be the specified yield strength of the steel. You have Pn, Vn, and Mn, which is going to be the nominal axial shear and moment strengths. And then we have Pu, Vu, and Mu, which is going to be the factored axial load, shear force, and moment as defined by the different types of loads that you are going to be placing on the structure. Other definitions here, we have epsilon mu, which is going to be the maximum usable compressive strain for masonry. An is going to be the net area cross-sectional area. D is going to be the distance from the extreme compression fiber in the concrete masonry to the centroid of the tension reinforcement that you would have. DV could be the actual depth of the member in the direction of shear. So if you have load reversals and stuff like that, then you maybe have to consider different depths that could be necessary. And then rho would be the reinforcement ratio that you would need. Strength reduction factors, phi. We're going to have those for different phi factors for different types of conditions. Here for reinforced masonry, combinations of flexure and axial load, we have 0.9. For shear, 0.8. For bearing, it would be 0.6. And then you could see the unreinforced masonry factors as well. We also have phi factors that we consider for connection capacity equations. So you can see those addressed here in the chart as well. For concrete masonry within the code, we know that we have a strength of masonry that is limited to 4,000 psi. We know that for grout compressive strength, we want to limit that to 5,000 psi. And then here you can see the different stresses that we can acknowledge for the potential tensile stresses, modulus of ruptures that would be used for, say, an unreinforced masonry check and design. You can see the different mortar types and mortar categories that give you different allowable stresses, so to speak, in the tensile capacity area. So next, you can see the reinforcement strength. Fy is going to be less than or equal to 60 ksi. Actual strength shall not exceed 1.3 times the specified value. And also the compressive strength of reinforcement should be ignored unless the reinforcement is tied according with compliance within the TMS code. There is some assumptions that we have to make. Looking at the linear elastic theory, plane sections remain plane. Stress proportional to strain, compatibility between masonry and reinforcement, superposition of stresses. Really making sure that you also obviously have that good bind between the grout in the concrete masonry elements and the grout to the reinforcement to make sure that you have, again, that good compatibility within the section. Factor design has to be less than the design loads that you have for your design. So flexural tensile stresses under factor loads must not exceed the modulus of rupture reduced by that phi factor, and then compressive stress under factor loads must not exceed the 0.8 times F prime M reduced by a phi factor. So again, more design assumptions kind of summarized here, that continuity between reinforcement and grout. We have equilibrium, we have sections remaining plane, and then different compressive stress limitations. Here's an image from the Masonry Society giving us different types of forces and stresses that you would have within your design. You can see that you have an overall force diagram that's going to give you stresses and forces in the section for different load applications. You certainly want to understand where the neutral axis is going to be. You can calculate the compressive force, see some of the moments that you have across the section. Really, for strength design, it really kind of comes down to this. Again, the factored design forces or demand has to be less than or equal to the strength or resistance for design. We have some code information here for design of a pier. We have the information here about the design for wall elements. We have phi factors that we want to consider for different strength design provisions, for flexure and axial forces, but then also a different phi factor here for shear and friction designs. Capacity equations that we have for walls. So we have compression capacity equations that we want to look at. If we have taller walls, we know that we have in height to H over R ratio of less than 99. We know that we have a reduction factor that's there. But if we have a higher, taller wall, we even have a larger reduction factor that would need to be utilized to account for the tall, slender capacities that you'd have for design. A useful value to know, though, also is to look at the if you don't have any height to consider, if you're just looking at the pure compression capacity, looking at what the actual forces are going to be for the design, so that your overall design is not going to be reduced by a factor, but then also looking at if you have a wall element where you don't have any ties containing reinforcement, we even can reduce the actual equation even a little bit further to the 0.8 times 0.8 times F prime M to the net area of concrete masonry minus any small areas of steel that you would have for design. So again, making sure that we understand what those overall capacity equations look like. Again, for a pier or column, anytime that we have ties, we can consider any of that compression that you would have in some of those different elements, or if you have piers, again, you can consider some of the compression that you would have in elements when we have lateral ties that are included. But anytime that we have wall elements where we don't have any confinement reinforcement, we certainly can't utilize any of the compression in those bar elements, those steel elements, for capacity purposes. One could say you could use, say, a pier design, a flush wall pier design. If you did put some stirrups or put some ties around some reinforcement, you certainly could do that, and you could look at an increased capacity by then utilizing the compression in the reinforcement by adding ties and additional reinforcement to that end. But I don't think that is extremely common practice for the design of walls. For strength design for reinforced bearing walls, we're looking at creating some, we're going to create a spreadsheet here. So just kind of looking at the overall capacity that you have for compression and then for bending moment, and kind of seeing what that interaction equation looks like for the different forces that can be placed on a wall. Really important to remember that when we look at the overall capacity sections, we remember that the reinforcement that we utilize within masonry walls, we do have a 6T or 3T to each side of the reinforcing bar as far as the maximum effective width that you can utilize for the capacity of, say, the compression block that you would use in combination to the tensile force that you would be able to justify for the reinforcement. So there is a limit to the actual width of concrete that you can utilize to determine the overall capacity for your design. That does not limit the spacing to be of the reinforcement to be 6T. It just limits the actual capacity side of the equation to that 6T for each bar in reinforcement. Kind of a little bit of a sneak peek here, looking at what the axial to moment interaction equation diagram would look like. We know that once we determine what the overall capacity line would be, we know that obviously any axial and moment forces that you would have, anything that's inside the curve is going to be acceptable. Anything outside of the curve is not going to be acceptable. So again, let's go ahead and see how we can build this curve to determine what the overall capacity would be. One of the first points that you would look at, again, is that pure compression. We're not going to be looking at any slenderness factors. We're going to be looking at pure compression, overall maximum capacity. It's going to be based on the equations that you see from the code on the right. But again, looking at the 0.8 times 0.8 times the F prime M times the overall concrete masonry compression area minus the small amount of reinforcement that you would need. Looking at, we should understand what pure flexure would look like. As before, the combination of compressive reinforcement is small. It can be neglected. So again, we look at our rho to be the area of steel divided by BD. So B going to be the width of the section. D is going to be the depth of the section from the reinforcement to the compression face. We can see what the omega would be there, and then the MN is going to be the moment capacity is going to be based on the area of steel times Fy times that set of equations that you can see at the bottom. So pure flexure, an alternate approach would be looking at what the A distance would be the area of steel times the Fy yield strength divided by 0.8 times F prime M times the width of the section B. And then from that, you can determine the overall, again, moment capacity equation. We also want to understand what the balance point would be. Looking at the neutral axis, you can look at the epsilon y for steel. You can look at Fy over the elastic modulus of steel to be 0.00207. We can look at then how that compares to concrete masonry, what the overall balance point would be when the masonry and steel are in that perfect kind of balance with one another. Next, we can calculate some of the corresponding tensile and compressive forces. You know that the tensile forces is going to be, again, the area of steel times the yield strength of the steel. The compressive forces are going to be based on the concrete masonry, so the 0.8 times F prime M times beta 1 times C, the depth of the concrete masonry, times B, the width of the concrete masonry block. And we know that the net axial allowable would be C minus T, any compression minus any tension. And then we can also see at the bottom there the overall moment capacity equation. So looking at this, just coming up with a simple example, we'll define what the overall moment axial force interaction diagram would be. For this design, we'll look at the design for an 8-inch concrete masonry wall, fully grouted, F prime M of 2500, number 5 bar at 48 inches on center, and kind of see what the overall interaction diagram would look like. Again, we want to calculate some of the different variables for our designs. And so you can see, again, calculate the position of the neutral axis corresponding to the balance point. And again, you can see D would be where the reinforcement is located to the compression face. C is going to be where that balance point is going to be between the epsilon mu for concrete masonry and epsilon steel for the actual steel that we're utilizing. So for any values of C less than the balance value, the steel will yield before the masonry reaches its maximum useful strain. And then combinations of axial force and moment corresponding to the moment or nominal capacity can be calculated as corresponding with the moment. So again, we can look at, again, how the different interaction equations are going to work here, the different values that are going to be utilized. So given the position of the neutral axis C less than or equal to the balance point, we can see that C is going to be equal to 0.8 times C times 0.8 times F prime M times B. Again, our tensile force is going to be AS times Fy. And you can see again what the axial and moment capacity equations would be. And then similarly for values greater than C, C greater than the balance point, the steel will be elastic when the masonry reaches its full maximum usefulness. So then we can again compute the corresponding stress and strain in the steel by proportion to find the different combinations for axial force and moment along the curve as well. So again, seeing what some of the differences are here would be, again, based on the masonry kind of reaching its full capacity first. So more equations, again, given the position of neutral axis C greater than or equal to the balance point, you can see what the resulting equations would be for axial capacities, moment capacities, beta in that is the ratio between the depth of the compression block and the distance between neutral axis. Beta C is denoted as A in technical references dealing with reinforced concrete. So A is equal to 0.8 times C. So with all of that built in, we can then determine, again, using a simple spreadsheet, we can look at the position of the balance point. We can look and see what the actual compression capacity would be, C. We can calculate that for all the different positions of C up and down the diagram. We can see then how our force in our reinforcement is going to be 0 for when it's mainly in compression, but then you can see the tensile force starts to develop as we get past the balance point, and then you can see the moment capacity as it's going to change with the different axial forces that would be allowed. So again, you can see the axial capacity, moment capacity, interaction line defined here for the overall design. So if we're within this curve, we know that our capacity of axial to moment capacity is going to be okay. If we're outside of the curve, we know that we're not going to be acceptable. It's also really good, again, to remember that as we move up, as you can see, as I have more axial stress and force on this section, we actually have more and more moment capacity. So you can see as the line increaser goes from bottom left to upper right, we're gaining more and more moment capacity. So when we talk about reinforced masonry walls, it really is true that the more load that you can put on those elements is generally going to be always beneficial for the overall design. There's going to be a point to where there is a point of diminishing returns, and you can start to lose moment capacity if you add too much axial force. But certainly that is going to give us a much better overall capacity if we can make sure that our masonry walls have some load on them. So again, getting back to so the different elements that we have for design, we're going to talk through how to develop this chart to what the primary different forces and stresses are going to be for these different elements. For designs, we'll start with the shaft walls, shear walls. Again, it's going to be governed by the axial compression to flexure curve that we just developed. And again, to the point of any time that we can add more load, add more gravity load to the actual design, we know that we can gain moment capacity by adding force. So if we can make them load-bearing elements, that we can certainly add moment capacity to our designs, which is going to make them much better overall design of the elements. We know that for basement walls, we do have axial forces. We definitely, if we can make them load-bearing walls so that the basement walls have even more axial forces, that can help the walls actually resist the out-of-plane bending moment that you're going to have on the design. You might have some in-plane shear wall behavior as well, but from the out-of-plane bending moment perspective, again, anytime that we can make exterior load-bearing walls down to the foundation walls, we actually increase and gain quite a bit of capacity. We also know that we have interior partition walls where we have minimal axial forces. Obviously, it's just going to be the self-weight, but here we also have very low actual lateral forces, pressures on the walls, so that we can rely on, in this case, sometimes we can have some unreinforced designs in addition to the reinforced designs. We know that that's going to change with different seismic design categories as we add more horizontal force. We know that we have more and more reinforcement demands, which again is really going to govern the overall design. But again, if we can get into an exterior wall, we know that we have, again, more and more forces that we can consider for the exterior walls if we could add actually load-bearing designs. Here you can see the non-load-bearing designs actually get a lot more reinforcement requirements because we're not moving up on that curve. We're still staying with pretty much a pure bending design situation. If we look at lintels and beams, really there's going to be minimal axial force here. We're really kind of stuck with designing that section for mostly primarily a bending for both the in-plane and out-of-plane direction, making sure that we have moment and shear capacities. Again, the benefit for lintels is we certainly can add overall depth to the design, increase the section, which certainly helps with the overall analysis and design. Columns and pilasters, obviously, we're going to have a lot of axial force generally coming down for those elements. So even if we have relatively high moments or lateral forces, we know that we also have a good helping of axial force to have us on the curve. So again, the overall building, we have the different chart. We have all kinds of different places where masonry elements can be used for the design. We know what some of the different primary forces are, but you can see here why adding more compression is certainly going to be very beneficial to the overall design of concrete masonry elements. So we want to make sure that we can maximize that by keeping our elements to be load-bearing designs for a variety of different conditions. We want to make sure that we can make sure that we always maximize that part of the design. We have a lot of different elements that go into the load-bearing walls. Sometimes we have openings, we have lintels. Within those designs, we also can have piers, we can have pilasters. So really these masonry elements are a combination of a lot of these different elements all within a single elevation. So where and how these forces flow through and pass through these different elements. It's going to be really important to have the right tools and software elements to be able to do this analysis and design. And then there's a lot of other attributes to masonry beyond the structural capacity. We know that architectural and aesthetics have a lot to do with the overall selection of masonry and how it's going to perform within a building. So, but certainly to the extent that we can utilize masonry to its full extent here by considering the right loads in our design. So with that, we're going to go ahead and wrap up. If you do have any questions, please feel free to reach out. Thank you.